All right, we're going to be studying some statistics here, and you've heard probably about the chi-square statistic that people find relatively difficult to understand, and it's kind of hard sometimes to understand why we're doing what we're doing. And usually the reason is you're not familiar with the data and why you're doing the things you're doing. So I thought I would start out explaining the statistics by using some data and some models that you may at least have a little bit of familiarity with. And then we'll transfer and say why we do things one way, and then when your data changes, you have to do things in a different way. And so I'm going to start out with grades. Grades are something that I think all of you kind of understand, and it will explain why you do the things you do with grades. And then we'll switch over and I'll say, well, you need to do something similar with the genetic data. But the genetic data, it's a different type of data. I'm going to explain something called shape in the distribution. And when you have different shapes in your distributions, you have different statistical tests that you have to do. And so you try to match your tests, all right, like the chi-square is a statistical test, and you match it to the distribution you have. We have a chi-square distribution. You use chi-square type tests. When you have a normal curve, like the one you're seeing here, you do different types of tests. And so I'm going to explain how the shape of your data leads to the model that you use, and then you try to do a test to see if it fits your model. And so here is your typical bell curve. You're probably used to this sort of thing. This is something you would see probably have seen your entire life. You have the A, B, C, D, F model for coming up with a fair way to grade your students. And as you can see in the true bell curve, there are only 2% A's, but there are an equal amount of F's. And the whole idea behind a model like this is that when you give a really hard test with lots of questions, the data will come out and you'll have very few people here and very few people here. The majority of people are here in the middle, and it's symmetrical. And the key for a normal curve is that you have this symmetrical shape. And if that's the case, if this is what your data looks like, then using a bell curve and using the A, B, C, D, F system makes sense. But it only makes sense if your data fits into this shape for the distribution. And I'll explain what I mean by that in a second. But if your shape isn't right, then you really shouldn't use this model. And I'll point that out here, and I'll make some rather, I think, funny comments on, I think it's funny, maybe you think it's kind of sad what we do, but our data doesn't fit this shape anymore. But we still, for historical reasons, use the A, B, C, D, F system. And of course, if you were doing this in this class, and we really did make it fit a bell curve, only 2% of you would make an A, and 2% if you would fail, and 64%, realize both of these are C's, would fit into the C level. You would also get the equal number of D's and B's. The interesting thing is, if you look at how people actually grade these days, almost nobody ever gives a D. It's like a non-grade anymore. Very rarely do you get D's. You get more F's than D's a lot of time. So it's kind of interesting how our culture has adapted to this system, and how this really isn't a very good grading system anymore for the actual data that you receive. But historically, this was an accurate one, and this actually started back in, I think it was like the early 1900s. I forget which school did it first, Princeton or somebody, came up with this ABCDF model, and then it spread to England and the rest of the United States. People thought it started in England, but it actually started here in the United States. And there are reasons to have this model to make it fair, so that you can compare, is someone an A really an A, And are they significantly better than someone who's a B? And is a B significantly better than a C, etc.? And do these people deserve to pass or fail? There are real reasons for using this model. If your data has this shape in its distribution curve. Okay, so let's go on to the next one and let's show a different version of this. This is something that the one we just saw has kind of evolved into something closer to this. And notice the shape is pretty much the same, but we've kind of changed the numbers. And the numbers, we give 10% A's, 15% B's, and 50% instead of 64% C's. But assuming that this is correct, that you're 10, 15 here, for this to work, you need to have 15% D's and 10% F's, and we don't get that. And this is called grade inflation. It's an occurrence, it's a real thing, and universities have been trying to fight this forever. But this grade inflation occurred starting in the 60s when they created more colleges and people were trying to avoid the draft, and because if you went to college, you didn't get drafted into the Army. And people would then go to college, and the professors and the administrations didn't feel right about failing people because they'd be sent off to the Army. It's all political and cultural in the United States, and it caused grade inflation. And then once you kind of let that genie out of the bottle, you never got it back in there. And so we've had this problem ever since about grade inflation. But let me show you an example of some real grades. Oh, I have to turn this off. All right, and all right. So you'll notice here I created some artificial grades, and this is legitimate. So you notice that it's symmetrical. So this is kind of like this graph here turned on its side. The graph under there. So you'll see how you have one here at A and one here, one grade, a 94 at A, and one grade, a 42 at F, and then 2 D's, 2 B's, and 6 C's. Well, this is legitimate. This model, or I should say this set of data, fits the normal curve or bell curve model, and it probably fits it very well. And there's a test you can use to see if your shape of your data fits a normal or bell curve, and it's called the Kolmogorov, let's see, I have it written here somewhere, the Kolmogorov-Smirnov statistic. And that statistic here is used to test, and if you have just some, say I created just some random numbers, well, it's very unlikely that a set of random numbers are going to give you this shape of distribution. And so you would do a test on that set of numbers, and depending on what that test tells you, you would know that yes, this is a good model for describing my data. And I can do all kinds of cool things and determine whether or not, say, my grading system is fair would be one thing. And if it fits the model, then this would be a legitimate, fair grading system. If it did not, if it failed the test, then you would look for a different model. And to kind of give you an idea of whether or not this set of data fits it, I'm going to pull up this. And here we see that we have 8% A's, 17 B's, 50% C's, 70% D's, and 8% A's. And so it's symmetrical. You got the 17 and 8 on either side with 50% in the middle. And that makes it fit this right here, which is kind of what you shoot for these days, I guess. You're trying to try to get your data. So you would probably be very happy if your grades turned out this way. And yeah, it would fit it would probably pass the Kolmogorov-Smirnov test. Of course, if you got it perfect, it would look like the data we had over here with 2% A's and 2. This is the perfect model, and you have no error in the system. This would be the perfect fit. This one doesn't fit that perfectly. You would still pass the test, but it wouldn't be a perfect fit. All right, and so that's the key for you to understand, that you don't have to have a perfect fit to pass the test. The test, it'll be a number, and if you get this particular number above or below a certain value, then you pass the test and you go, okay, this is still fits the normal curve model. I think it's fair for me to give A's, B's, C's, D's, F's under this model. If you get a different shape that's completely different, then that's probably, it won't pass the test, and it's probably not fair to use the ABCDF model. And so I'll give you an example of where it wouldn't be fair is under our current system. This is probably what we get today. After the 60s, 70s, 80s, 90s, 2000s, etc., you went and you started seeing this. This is called a bimodal distribution, not a normal distribution anymore. And this requires a different type of grading system. The ABCDF grading system doesn't make sense when you get this shape of a curve. And the bimodal system is conducive to pass-fail. This should be passing and this should be failing. And we've tried that, and people don't like that. They would rather get an ABCDF, and historically that's what we've used. So this doesn't usually go over well, and employers don't like it. They don't get to be able to say, I want to know more than if they just passed. I want to know the whatever. But this actually would be very good for pass-fail, and that's why people have tried to use pass-fail instead of ABCDF. But what happens is you get people who made a B, but they were doing almost exactly the same work as a person who made a C, or maybe they're making a B and they did almost exactly the same work as an A, but they get hugely penalized. It's just arbitrary. In other words, the grading systems are arbitrary. They're not based on how the distributions actually work. So it's probably an unfair system, but historically and politically it's hard to leave the ABCDF system. It's been around too long. But actually probably with today's college grades, everything should be pass-fail, according to the statistics. And in high school, it's kind of reversed. Now, this is kind of scary to maybe most people if they knew this, but this is what you get in college these days. You get lots of these grades and fewer, but still a significant number of these. So pass and fail. But if in high schools, this is what you're getting. You're getting a few people passing over here and lots of people failing. And of course, you can't fail everybody. You can't fail anybody in high school anymore. And the reason is because this is the shape of your data. So essentially, you get, instead, what they do is they take the people who are here and they try to put them in, say, advanced classes, and then they just leave everybody over here. And that's really what the political result of this is. But you can see it in the statistics. And these should be the people passing, and these should be the people failing. And, unfortunately, the politics don't let you fail anybody, so it's a mess. That's all I can say. But it's kind of interesting to know how what the statistics say about all of this, and you just don't hear this. Now, how does that relate to us? Well, we are going to use the chi-square statistic, and the chi-square is good for modeling genetic data. That was grade data, and you're familiar with grade data. You know how that works. All right, you're probably not familiar with how the genetic data is shaped and what models you should use. You have to use a different model with genetic data. With genetic data, you kind of use this thing called degrees of freedom, which I will explain in another video. But the idea is, depending on how the nature of your data, you might have different degrees of freedom. It depends on how many variables you have. In other words, variables being how many traits you have, like purple and white. So with purple and white, you have 1 degree of freedom, because it's always how many variables you have minus 1. So it would be 1 degree of freedom. If you have 3 colors, maybe you have black, white, and brown, all right, as your 3 colors, kind of like hair color. And so you have 3 distinctive colors. And that would be 3 variables, or 3 possible phenotypes, or 3 possible, I shouldn't say traits, I should say phenotypes, 3 particular traits for that character. Character would be hair color, and then you would have 3 particular versions of hair color: brown hair, blonde hair, and black hair. And so that would be 3 potential outcomes. That's another word you could use. We subtract 1, and that gives us a 2. which is the number of the degrees of freedom. So if we had a genetic cross and it had a distinctive heterozygous phenotype, where you have big A and little a, and it gave a distinctive color that was different than two big A's or two small A's, homozygous dominant or homozygous recessive, then we would have 2 degrees of freedom, and our curve would look like this orange one here. If we had 4 degrees of freedom, all right, you would get a curve that looked like this, and 10 degrees of freedom actually looks kind of like our bell curve. It's skewed to one side, but with 10 degrees of freedom, that means 11 characters or 11 traits for a character or something like that. You would actually get something that kind of did look like a bell curve. You probably still wouldn't pass. Oh, this might begin to pass the Kirchhoff-Smirnoff if it were occasionally, but it would still pass the chi-squared. And so there is a chi-square statistic that says, is my real-world data, does it fit my model? In other words, is the data I'm getting fit into, is it shaped this way? Just like are your grades, where the grades shaped like that bell curve when you looked at the distribution. All right, well, in the chi-square statistic, it works a little different. You have a different test than the Kirchhoff-Smirnoff, Kolmogorov-Smirnoff test. All right, instead we use the chi-square test, all right, and the chi-square statistic to see if our data is actually fitting these shapes, all right, and in our distribution. And of course, we're also looking at ratios. We're not looking at distinctive things, but I will get into that in the next video. This first video is just kind of giving you a background on kind of the big picture and to compare it to something that you're probably more familiar with, which is the normal curve and grades. Because we're doing genetic data, it comes out with a different shape in its distribution, all right? And so therefore we have to use a different test. We can't use the one you would use for a normal curve. We have to use the one you use for a chi-square, all right?